Hello, everyone. My name is Qicheng. I'm from Actel of Carnegie Mellon University. Today, I'm going to introduce our work named LAIDAR, a learning method aiming for accurate IC diagnosis with ideal resolution. The diagnosis we focus on mainly refers to logic diagnosis of digital circuits. In a typical diagnosis process, a software diagnosis tool will take in the field log from testing and the circuit description. A field log records the test responses of a fading chip. The output of diagnosis is usually a list of defect candidates corresponding to a certain location in the circuit with the defect characteristics. And according to the result, PFA, physical fading analysis, can be performed to further inspect the potential defects. The quality of diagnosis is usually characterized by two metrics, resolution and accuracy. Resolution refers to the number of candidates reported for each defect, and accuracy indicates whether any reported candidate corresponds to the actual defect. Unfortunately, due to the design and fabrication complexities, such as the existence of multiple defects, it is quite often that diagnosis ends up with an inaccurate result, which directly leads to a waste of PFA resources or a bad resolution that makes it difficult to pinpoint the actual defect location. All these can significantly slow down the progress for yield learning. Many machine learning-based methods aim to train a classifier to predict whether a candidate corresponds to the actual defect. Different from other methods that trains the classifier based on simulation data, PADRE, one of our previous works, uses real diagnosis results for model training. The main idea of PADRE is to train a classifier on the on the candidate level, meaning that all the candidates are put together in a pool for training and prediction, regardless of its corresponding defects. Each candidate is predicted with a label on either good or bad. Here, good means the candidate corresponds to the true defect, and bad means not. The bad candidates will be removed from the candidate list and thus improve resolution. However, PADRE's classification performance is compromised by the labeling error caused by its intrinsic labeling process and limited training data. For example, in one circuit, 1/7 of good candidates are incorrectly predicted as bad, which directly decreases diagnosis accuracy. On the other hand, we found that there are other potential information not being fully used, like the correlation between labeled and unlabeled data, as well as the defect level information. Therefore, we developed a more advanced method, LAIDAR, to further enhance diagnosis results towards a higher quality, in which semi-supervised learning and defect-level learning are deployed. And in this paper, we also explicitly discussed the trade-off between accuracy and resolution to provide practitioners with guidelines on how to tune the ML algorithms for a specific objective. So before introducing LAIDAR, I'd like to first briefly introduce some preliminary information. We usually use a confusion matrix to describe the performance of a good-bad candidate classifier, where each entry represents the number of samples with a true label and a predicted label. The bottom left corner refers to the number of actual good candidates being mistakenly predicted as bad. So a high accuracy requires this number to be small. The top right corner, in contrast, represents the number of actual bad candidates being mistakenly predicted as good. Therefore, to improve resolution, this number should be small. However, when tuning an ML model, it is virtually impossible to minimize both the bottom left and top right entries, because adjusting the model parameters usually decreases one entry while increase the other. The trade-off between the two entries corresponds to the trade-off between accuracy and resolution. The second aspect is the features we use for LAIDAR. They are mostly the same as PADRE, therefore it's not the main contribution of our paper, but it will be helpful to get a sense of what information LAIDAR uses for prediction. If you are interested in the details or the full list, please refer to this paper here. So the overall flow of LAIDAR is divided into 4 stages. LAIDAR takes in as input the original diagnosis result from a population of failing chips. Each sample in the input data set contains the extracted feature of a certain candidate and also includes the corresponding defect information. At first, all the samples are unlabeled, and in the initial labeling step, part of them are labeled by 2 rules, and then semi-supervised learning is adopted to use both the labeled and unlabeled data to train a classifier and predict for all the samples. Then, the defect-level learning process follows to make a good use of the correlation between similar defects so that to identify some obviously bad candidates to further improve resolution. Finally, a calibration procedure is employed to ensure accuracy. For example, if all the candidates of a defect are labeled bad, then all of them will still be kept in the list to assure accuracy. For initial labeling, we use 2 rules. We first label all the inconsistent candidates as bad. Inconsistency indicates the candidate has neighborhood net states for at least 1 TPSF pattern and at least 1 TFSF pattern. PADRE excludes these samples from training, but we show in the paper that they are actually very useful. The second rule is that if a defect has resolution equals 1, then the only candidate will be labeled as good. On the other hand, if the resolution is larger than a threshold Q, then all of the candidates are labeled as bad. In this way, only 1 candidate, which corresponds to the actual defect, will be mislabeled. The larger Q is, the lower the mislabeled ratio will be. But at the same time, fewer samples will be labeled for model training. Since we have much more labeled data generated by Rule 1 compared to PADRE, we are able to use a much larger Q to achieve a lower mislabeled ratio and guaranteeing a similar amount of labeled data. After initial labeling, we have 2 sets of samples, the labeled set and the unlabeled set. Supervised learning method will train a model based only on the labeled data. However, the distribution of unlabeled data and the correlation to the labeled data can also facilitate model training. Here's an example. If we only train a model on the labeled data, we may get a model that does not perform so well due to data insufficiency. However, if we also know the distribution of unlabeled data, then it is possible to get a more reasonable decision boundary. The learning method that uses both labeled data and unlabeled data is called semi-supervised learning. A variety of algorithms have been developed for SSL. Self-training is one of the earliest and most straightforward algorithms. It performs the best for this application with best computation efficiency. As the name implies, self-training leverages the predictions on unlabeled data to obtain additional information for decision boundary calibration. It is a wrapper method based on a supervised model, which in our case is a random forest. Here is a simple illustration of this procedure. In step 1, we train a random forest model, model 0, based on the labeled data, and then use model 0 to predict for the unlabeled sample in step 2. Each unlabeled sample is predicted with a probability. A higher number means it is more probable for the sample to be a good candidate, and a lower number means more probable to be bad. In step 3, all the unlabeled data with a predicted probability larger or smaller than 2 thresholds are labeled as good or bad respectively, and will be used as label data for a new iteration of training in step 4. In step 4, the updated label data are used to train a new model, and the iterations containing the above steps will continue until no more confident predictions can be found. During self-training, the decision boundary is expected to gradually improve as more and more unlabeled data become labeled. And we use strict confidence in threshold to ensure high fidelity predictions are used for training in subsequent iterations. So previously, all the candidates are put in the same pool and treated independently. Defect-level learning is at a higher level than candidate-level learning. That is, instead of treating all the candidates in the hyperspace independently, candidates are now grouped with their corresponding defects. The motivation is to uncover and utilize the correlations that exist among similar defects. Specifically, it is assumed that the defect with similar sets of candidates have correlations between their good and bad candidates, which can be leveraged to improve diagnostic outcomes. For example, in this plot, the points with the same color are candidates that correspond to the same defect, and the larger ones are the good candidates. These are defects with similar candidate distributions, and we can find that the good candidates are close to each other. So it is possible to eliminate some bad ones that are far from them to further improve resolution. Then the question becomes how to find the similar defects. The similarity between 2 defects is determined by the distance between the distribution of 2 sets of candidates in the high dimensional feature space. If we can have a distance measurement that measure the distance between the 2 candidate distributions, then clustering algorithms can be used to identify the similar distributions. We use an estimator for range divergence to define the distance between 2 candidate distributions. The performance of LAIDAR is evaluated via 2 experiments. The first one uses a virtual dataset constructed from comprehensive simulation. Since it is a virtual dataset, we know the ground truth label for all the samples. In the second experiment, LAIDAR is applied to the diagnosis outcomes from actual fade-in chips from an industrial design. For this dataset, we do not have ground truth for all the candidates, but we do have 6 PF8 chips that have the actual defect information. PADRE is used as a baseline method for comparison. In the experiments, both LAIDAR and PADRE are applied to improve the diagnostic resolution of initial results from the diagnosis tool, and then evaluated and compared in terms of resolution improvement and achieved accuracy. The final calibration step of LAIDAR is also implemented for PADRE. Here, the left figure gives the defect level resolution improvement produced by LAIDAR. Note that the number of defects with perfect resolution increases by 6.4 times, and the number of defects with resolution 2 increases by 2.4 times. The performance of LAIDAR and PADRE are compared in the right figure. It shows the number of defects with resolution improvement from 0 to 9 through PADRE and LAIDAR. Nearly 800 defects have no resolution improvement after applying PADRE, but the number is 200 lower for LAIDAR. LAIDAR also shows advantages for the number of defects with resolution improvement that ranges from 1 to 9. In addition, note that the largest resolution improvement resulting from PADRE is 91, while the number for LAIDAR is 207. These heat maps compares the number of defects with an initial resolution and an improved resolution. For each heat map, The resolution is divided into 6 bins. The diagonal elements are the number of defects without bin-wise resolution improvement, and elements below the diagonal are defects with bin-wise improvement. The left subplot provides the result for the accurate cases. Compared to PADRE, LAIDAR has lower number for diagonal elements and larger values for under-diagonal elements, indicating that LAIDAR significantly improves resolution over PADRE, especially for defects with a large initial resolution. The right subplot provides the result for the cases that are inaccurate. LAIDAR produces only 3 cases, while PADRE has 68. Also, the 3 inaccurate defects for LAIDAR retain a high resolution, which means these defects are unlikely to be used for any further analysis, so they are not harmful. In contrast, the inaccurate defects resulting from PADRE have a very low resolution, implying that resources for volume diagnosis and PFA will be wasted. Now let's take a look at the Silicon Dataset. The left figure shows the resolution improvement at the defect level through LAIDAR, where the number of defects with perfect resolution increased by 50%, and the number of defects with resolution of 2 increases by 54%. The original resolution and the improved resolution for the 2 methods are shown in this table with respect to the 6 PFA chips. When PADRE is applied, the true good candidates for 3 chips are incorrectly predicted as bad. LAIDAR, on the other hand, improves resolution while preserving accuracy. In summary, accurate and high-resolution diagnosis is essential for efficient PFA to identify and understand the root cause of IC failures. LAIDAR is an advanced diagnosis enhancement methodology that is equipped with multiple machine learning technologies. Semi-supervised learning exploits information from unlabeled data to augment model training. In addition, a defect-level learning procedure utilizes information from similar defects to further improve resolution. Experiments on both virtual and silicon datasets demonstrate that LAIDAR not only significantly improves diagnosis results, but also consistently outperforms the baseline method PADRE with respect to both accuracy and resolution. Moreover, this work has explicitly exposed the relationship between ML metrics and diagnosis qualities, specifically the trade-off between accuracy and resolution. More details in this aspect are introduced in our paper.